All right, let's get started. Thanks everyone for coming to lecture. Today we have a kind of a thematic lecture where we're going to first cover that forward and backward algorithm that I did not cover very well at the end of last lecture, the E&M training algorithm for unsupervised training of HMMs called the Baum-Welch algorithm. And then we have a guest lecturer or a guest speaker, guest lecturer today, who will cover speech and dialogue systems for about, I don't know how long she'll go, but up to 30 minutes. And then afterwards, we have a section on transformers where I kind of blitz learned transformers yesterday and the day before, so I can lecture it. And then it's also relevant for my task too. So it'll be useful for all of us. As a quick reminder, for assignments, your project 2 visualizations are due today, and then your report is due tomorrow. If you need an extension on those, just let me know, but it's like a group project, so you should be pretty close to finish now. I know we've been a little bit slow on the Piazza, so I apologize for that, which is why I'm willing to be a little bit more lenient with the deadline on this one. But I also don't think it was relatively straightforward. So hopefully you were able to complete that on time, and then you won't be behind on the next homework 6, which is mostly on HMMs and these kind of topics. Okay, any questions on course logistics? Cool. All right, so let's talk about HMMs real quick. So as a quick refresher, HMMs are these kind of special formulation of naive Bayes models where not only do we have these emission probabilities of probability of x given y, we also have these transition probabilities of one y conditioned on the previous y. And so we're modeling this joint distribution based on these assumptions that each x is only dependent on its corresponding y, and each y is only dependent on its previous y, right? So, and based on these kind of conditions, we showed that we can do tasks like part of speech tagging using supervised training, right? So if we kind of recall, let me go through here. So this is the Markov chain diagram that we covered, and then each of these elements that are on the screen, right, you store in some matrix, and that way, instead of having a massive model that memorizes the entire joint probability distribution, you only have to memorize these, and that's far less complex. So quick reminder of the matrix formulation, because that's what we're going to be using as we talk about the forward-backward algorithm, right? We can define some transition matrix A that stores all the transition probabilities. So for the part of speech tagging example, the probability of a noun coming after a verb, coming after a noun, coming after a noun, etc. And then we also have this observation matrix where we're storing all of our emission probabilities, which is the probability of the word fish conditioned on noun and the probability of fish conditioned on verb, etc. And we noted that this is kind of backwards of what the task is, right? The task that we're trying to predict is probability of y given x oftentimes, but then we covered the Viterbi algorithm on how to calculate that using these probabilities, using some dynamic programming tricks. And this way, we also don't have to learn transition probabilities between words, right? That's what we're trying to avoid. We're trying to not memorize fish after bird, fish after dog, fish after sleep, all those probabilities, because that blows up the complexity of our model. So supervised training was quite easy. We just maximize the likelihood by counting, right? So we just go through our training data set and we just count how many times each transition occurs, so how many times noun comes after noun, etc. And then also we just count our emission probabilities, so the number of times fish is a noun, etc. So we just count that, and that's all supervised training was, and that's the exact same thing as naive Bayes. So then we motivated then into unsupervised training. So oftentimes in these kind of tasks, especially in these language tasks, these NLP tasks, supervised data is really hard to acquire, right? So if we were doing POS, then you would need a collection of sentences and parts of speech. Whereas unsupervised data, so just straight up text, is really plentiful, right? We have the entirety of the internet that we can scrape from. And so it'd be great if we could train this HMM on just the data and not the labels. So that's what we mean by supervised training. But we still want to estimate px comma y. We still want to estimate this entire joint distribution because we're treating kind of y as this latent variable, right? We're treating this y as this hidden state vector that can be learned from, well, not that can be learned, but we're still including it in our assumptions because the HMM structure provides a lot of useful properties. So then the question was, how do you train an HMM with just x and not y? Where, again, looking at the graph, where's the graph? There it is. Where x are the observations and y are the hidden states. So then the kind of setup that we discussed was that we're only given x in this unsupervised case. But if we had y, right, if we had all the labels, we could just use maximum likelihood to learn A and O. We can do the counting thing to learn the emission probabilities and the transition probabilities. But if we had the emission probabilities and transition probabilities already, if we had a trained model already, right, given x, we could predict some y, right, based on some given x. So this is the chicken and egg problem that we're setting up, and this is the same formulation that allows us to use an expectation maximization algorithm to kind of learn both of these parameters by alternating back and forth. And we saw that in previous lectures as well. So let's kind of go through this EMM algorithm, this Baum-Welch algorithm. Baum-Welch is the EMM algorithm specifically for HMMs. And let's go through this algorithm, and we'll go through each of these steps in detail. So I'm going to spend a lot more slides on this than I did on last lecture, essentially. So what we're going to start with is we're going to randomly initialize A and O. We're going to randomly initialize these transition and emission matrices. And this is kind of the similar thing, again, that you saw in collaborative filtering models, where we just randomly initialize the model to start with. And then for each given sentence, or for each given sequence in some training set, right, what we're first going to do is we're going to predict the marginal distributions of y conditioned on the entire input sequence, right? So this is the probability that the second y is a noun. And I'm going to keep using POS here just because it's convenient, but like this is kind of detached from part of speech tagging at this point, right? Like y doesn't necessarily mean part of speech, but I'm just going to keep using that term just because it's easy. But we're going to predict that y is a noun given the entire input sequence from x1 all the way to xl. But note that it's not just y; it's like yi, right? So we need to predict the probability, model the probability of y at the second position based on the entire input sequence x. So that's the expectation step. We're calculating y given this randomly initialized A and O, right? These randomly initialized transition and emission probabilities. And then based on that y, we can count, quote unquote, these predicted y's to estimate a new A and O, right? And I say count because these are now like probabilities, right? These aren't like y is noun verb, like we can't count it like that. But instead, we can kind of treat it similarly and just add up. It's like a soft sum almost of the actual probabilities. So again, expectation, we're getting y from A and O, from some randomly initialized A and O. And then maximization, we're then learning A and O from that y, right? And so if we do this repeatedly and based on some corpus of data, right, based on some collection of training data of sequences, then the idea is eventually this process will derive out some kind of structure in the data set itself, and that it will converge at some A and O eventually that kind of describes the joint probability of that input data, right? So this is, again, kind of similar to the collaborative filtering example, right, where we went through each data point in our training set, and we kind of iteratively update our parameters step by step. So like I mentioned, we have these marginals. So these marginals are actually harder than you might initially think, right? So up till now, we've been able to fairly easily calculate kind of any kind of conditional probabilities using the emission and transition probabilities. But this marginal that we need to calculate here for the expectation step, we need to predict y given the entire input sequence, right? So it's not just the x up to the position of y, but also the x future, right, past y in the sequence, and kind of all of that information needs to be gathered when we're calculating that marginal probability. So this is where the forward and backward algorithm comes in. It's just during this expectation step. So let me kind of formalize this a little bit because I didn't think my previous slides from last lecture had this. So solving this E step, again, requires computing these marginals. So one example might be, what's the probability of Y3 being a noun given, the entire X sequence, right? So note that, again, it's not just up to here. And previously, following the arrows, you would say, well, Y3 only depends on Y2 and X2 only depends on Y2, so blah, blah, blah. But in this case, because we need to calculate this marginal probability where we need to be dependent on the entire input sequence X, this can get complicated. So some naive way of doing this might be to go through every single possibility, right? So, if you just go through every single possible, Y sequence, you could calculate it, and then you could calculate the marginal that way. You would essentially have to marginalize the entire input sequence X, but that's computationally untenable. So instead, what we're going to do is we're going to take advantage of some kind of clever tricks to derive out this forward-backward algorithm. So again, here's the marginal probability that we need to compute. And we can note that, so first of all, so note that since X is given, and we've used this trick before, Y given X is actually proportional to just the joint distribution Y comma X, right? Because X is fixed, right? So we can just softmax over X later. That's easy. Okay, then what we're going to do is, and you might kind of notice this from the Viterbi algorithm, which is that we're going to take this yi x y to l joint distribution, and then we're just going to split up X, right? And so you can see how that conditioning on just the entire input sequence is the same exact thing as conditioning on, or not conditioning on, but being joint with two pieces of that same sequence, right? So if we say I is 3, so for Y3, right, we take this sequence, chop that up, and we take this sequence and we chop that up. So that's pretty straightforward. Oh, I had boxes. Okay, so I have colored boxes here to show what parts of this model that we're covering. And then what we do is we marginalize. So we marginalize out yi and x1 to I out, so that now this becomes a product of a conditional probability and disjoint probability. So that's just probability, right? So that part should make sense. And then the claim that we can make here that simplifies this entire problem is that X, this part, is conditionally independent of this part. So going back to my boxes, right? Given yi, right? Because we're saying is Y3 noun, whatever, right? So if we give Y here, then we can claim that this green box, or at least this purple box, is conditionally independent from this green box. And so what we're trying to do is we're trying to drop that element from that probability definition. And kind of the logic behind this is you can go through this mathematically, of course. You can write out all these arrows mathematically and show that these are indeed conditionally independent. But the other thing you can do is you can kind of try to get from one block to another, right? And this is kind of a graphical technique where you say, okay, how do I get from this purple box to this green box in this diagram when Y is fixed, when Y is given, right? So the only path to go from purple to green here is through these arrows, but this is fixed. So this path you can't go into, right, on this graphical Markov chain diagram. And then also, if you want to go from green to purple, right, again, because Y is fixed, this Y is this bottleneck here. So these, you can't go from green to purple, and then you can't go from purple to green, essentially. And so we can kind of show graphically, at least, that these two things are conditionally independent. And therefore, we can drop that element from our distribution, and we're now left with this really nice conditional probability where it's the probability of x1 I plus I plus 1 through L to the end, conditioned on yi, right? And then dependent on yi, and then the joint distribution of yi and this, and all of the previous x's. So that's why we call this the forward-backward algorithm, right? So, this distribution goes forward, right? And then this distribution goes backward. And there's also some message passing theory that you can do this with. but I'm not going to go into that because that gets pretty complicated. So again, we can define these each of these parts as alpha and beta, and then finally we can just compute the marginal by combining the two terms and multiplying them. And then this is just that. Remember, we made that proportionality assumption, so we're just softmaxing. That's all this sum is. And then you can do this for the transition probabilities too. I'm not going to walk through that just because it's really long, but just know that given this forward and backward part, we can calculate not only the emission probabilities, but also the transition probabilities. And finally, you might notice that this setup is ripe for some recursive definition. So then the point of these next two slides is that this forward part and the backward part can be defined kind of recursively, and therefore we can use dynamic programming to do these more computationally efficiently, right? So for each, when we're trying to solve for every I, naively you would recalculate this whole thing for I over and over again. But instead, if you start from 1, right, so y at 1, and then each I plus 1, kind of, you can reuse a lot of the output from the previous step to calculate it out. I won't go through this too much extensively. You can come back to the slides if you want to go through the equation and make sure they work. But the point is that forward and backward you can do with dynamic programming. Same thing here. Yeah, same thing here with the backward. Again, naively, you would just do this, calculate the whole thing out for I every single time. But if you start from the end, so if you start at the end and then you work your way forwards, you can define this recursively and you can do dynamic programming. So again, the forward part literally runs forward with the dynamic programming. The backwards part literally runs backward with the dynamic programming. And then for each training example X in your training set, you just compute this. So that's just the expectation step, right? So that's getting Y's from your A and O, right? So now we have pseudo labels for our data, kind of. You can treat it that way. And then now we do the maximization step, which is just counting, right? It's just counting, but instead of this indicator function 1 of how many times does this occur, it becomes this probability that we define, the sum of these probabilities. All right, one quick note on initialization. So previously, for the part of speech tag, or for the tagging problem, we chose the number of hidden states based on the number of tags. In this case, you can have as many hidden states as you want, right? Because it's just going to fill them up. So by hand, if you know how big your problem is, you can define it, or you can use some kind of cross-validation to check how much dimensionality you need. So that's it. That's all of unsupervised training for HMMs. So again, I hope I explained it better this time because I wasn't rushing through it in 10 minutes. But again, now we can train an HMM just based on word sequences. Y itself are hidden states. All the pairwise transitions are through the Ys. And we can train this using the ENM algorithm and converge to some local optima, just giving our training data. Okay? Yes? Yeah. So once you go long enough, it'll converge just because you have a limited training set. So eventually it'll converge on some. So there is an optimization guarantee. I won't go over it, but yeah, I would say that there is because the training set itself is limited, right? So it's gonna converge to something. Yeah. Oh, the expectation step. Sorry. So during the expectation step, we need to calculate these marginals, and therefore we use the forward backward to calculate that marginal. Yeah. Mm-hmm. Yeah. Sorry, I wasn't clear enough on that. Yeah. So I use part of speech because that was the example that we had before, but it's going to learn some latent space representation for Y that's useful for that language modeling, right? So not necessary. So Y's won't correspond to part of speeches anymore. It'll correspond to something that it figures out is useful. It's like latent space models. It's like the collaborative filtering matrix factorization models as well, right? Where we don't know what it's locking onto, but it's just using that dimension to store information. Yeah, and you're going to do that for project 3, so you'll see. Yeah. All right. Any other questions on unsupervised training for HMMs? Great. All right. So now we're going to move on to our guest speaker. Okay, so this is Jessica Hoon. She's a PhD student at the Carnegie Mellon University Language Technologies Institute. Her research interests are in harnessing information from speech and text in order to effectively communicate with groups of people with adaptable dialogue systems. She was a program committee member of the Human Evaluation of Generative Models workshop at Europe's 2022, and she's also a NSF Graduate Research Fellow. We also went to college together at Columbia. So she was visiting for a conference, so I asked her to kind of speak on dialogue systems because I have no expertise in this area. So please welcome Jess and thank her for taking her time to do this lecture today.
All right. Hi, everyone. All right. Thanks for the kind introduction, Jake. So yes, as Jake said today, I'll just be giving you a brief overview of dialogue systems and speech tasks. Let's see. All right, there we go. And Jake already kind of said this about me, but I'm a PhD student at Carnegie Mellon University in the language. And so I've recently done work on crowdsourcing and dialogue evaluation, and now I'm doing work in the HCI sphere and also work with large language models. So yeah, my interests lie in like dialogue, speech, and human-computer interaction. So here's some just background on early dialogue systems. So I don't know if you guys have heard of this system called ELIZA, which was released in 1966, so it's quite old. And ELIZA was a rule-based chatbot that mimicked a psychologist. So as you can see here, the patient would say, oh, men are all alike. ELIZA says, in what way? Patient says, they're always bugging us about something or another. And ELIZA says, can you think of a specific example? So as you can see in this example conversation, for each sentence in the patient, ELIZA actually determines a pattern that the sentence follows and then acts upon it with the rule associated with that pattern. So these kind of patterns can be associated with specific keywords such as something, which I highlighted here. And there's an order of importance which these rules are executed, since more than one rule could apply to a sentence, as you would imagine. So ELIZA also stored bits of the conversation as memories, which it would use to reference later on in the conversation, which was this very early user personalization. So these are more of the modern dialogue systems that I'm sure you all have seen with Alexa, Siri, and Google Assistant. And so we've used these systems for simple tasks such as asking for the weather or searching for a piece of information on the internet. Like for example, you can ask Alexa, set a timer for 5 minutes, or Alexa, turn on the lights. There's also been some work with Alexa Prize competition where it's for competing to build like an open domain chatbot system. So with all these dialogue systems, what actually goes into building these systems? Before that though, there's like two large types of dialogue systems. One is task-oriented, which I talked about before, of what you were using Alexa for, and also open domain chat. So each has its own set of goals. On the task-oriented side, the main goal of the conversation is to complete a task. So some of the commands I gave earlier, like for example, if you want to ask Alexa for the weather, those are the task-oriented tasks. These conversations are mostly limited to a particular domain. So let's say if you're asking a system to book a restaurant for you, you're most likely only going to be asking for that throughout the entire conversation. These systems are also focused on obtaining information for the task. So for example, if you're going back to booking a restaurant, the system will want to ask you about the restaurant name, the time, number of guests, etc. But on the open domain side, there are no explicit goals to the conversation. It's just aimless chit chat. The user could bring up any topic like current events or books, movies, etc., and also wants to be continually engaged in this conversation. So these kind of chat systems cannot be dry, whereas in a task-oriented setting, a more concise system may actually be more beneficial. So there's also two main ways of approaching coding such a dialogue system. So there's modular systems and end-to-end systems. So I mostly work in the modular system space, so I'll be talking more about that. So you can see an example of the pipeline of a modular system here. So you give the dialogue system some sort of utterance with speech. This could also be with text. The model will then go into the automatic speech recognition module, which will transcribe speech into a piece of text. Then we will go into the spoken language understanding or the natural language understanding module. And this translates this text into potentially slots. So the slots are the information that's important for a task-oriented system, say the restaurant name or the time, or maybe how the user is feeling. I'll elaborate on this more in a bit. There's also been work which combines the ASR and the NLU aspects into an end-to-end SLU framework, which slightly mitigates this propagation error. So the propagation errors, you can see there are 5 different modules, main modules that are present in these modular dialogue systems. And you can imagine if the system messes up in the ASR, then this error is going to propagate into the NLU, the dialogue manager, and it could affect that system output later on. So after the SLU and NLU, we have this dialogue manager. So the dialogue manager handles all the information that we gained from the user and makes a decision on what the system should do. Then we have the natural language generation and the text-to-speech, which will output the speech from the system. So I'll go more into depth about the SLU and NLU parts, dialogue manager and natural language generation, and then later on I'll talk about the speech aspects. Oh, okay. Oh no. Okay, there we go. So talking about this more in depth, there's several tasks that are within this spoken language processing, natural language processing state. So the first one will be semantic parsing. So semantic parsing is when you receive an utterance as the input and you parse it for certain information. So we have, we have this data set, the spoken task-oriented parsing data set, which you can search up later. And it actually parses the utterance into intents, slots, and slot values. So what intent is intent is used to determine what the user wants to do with this utterance. For example, going back to the restaurant booking, the intent could be that it wants to provide the system with the time for the booking. The slot and the slot value provide the actual information for the system to complete the task. So that would be the actual time in that case. Next, we also have the task of emotion and sentiment analysis. So some data sets here are IMOCAP and MELD. So IMOCAP is a data set where people act out emotions, while MELD consists of dialogues from the Friends TV show that are annotated for emotion. So the task here is given an utterance in a conversation, figure out what emotion that the person was conveying in the utterance based on the entire context of the conversation. Then we have intent classification. So I talked a little bit about what intents are. And the main data set here is the HIS data set, which is the Airline Travel Information Systems data set. And here, this is people asking about flight information. So you can tell there's a lot of potential intents there. Lastly, we have the dialogue acts. So the dialogue acts are a little bit different from intent. It actually describes more the purpose of the utterance rather than the intent. So some of these examples are statement, non-opinion, yes, no question, WH question, etc. So here's some areas of exploration that I've kind of been thinking about. So the first one is the emotion. So emotion is still very difficult to define, as you might think. So it really depends on a person-by-person basis, how they perceive emotion, how they portray emotion, and this just depends on the person. There's also tasks that have limited amounts of data. So you can imagine maybe in the restaurant domain, you have this specific intent and you only have one example for that. But you still want to be able to classify any way that a user might want to portray that intent. There's also the issue of long context. So with the dialogue, many models have this limit on how long the input text can be. And as you can expect for dialogue, you could have a long dialogue context. And this brings the question of kind of how can we summarize or format the long context in a way for the model to be able to use all that information. So as a side note, I know Jake is going to talk about transformers later, but I'll talk about it a little bit here with one of the models called BERT. So BERT is the bidirectional encoder representations from Transformers paper, which was published in about 2018, 2019. And it was a huge leap kind of after Transformers were introduced in 2017. And a lot of the other models that I'll discuss later have been built off this transformer architecture, and they achieve high performance on these natural language processing tasks. So just to go over the two training tasks that BERT uses. First one is the masked language model. So what they do is, let's say you have a sentence, you replace certain tokens in that sentence with a mask, and you have that model predict the masked words in order to kind of look at the context around it. Next, we have the next sentence prediction. So what this does, it predicts the next sentence. So there's a binary yes or no if the next sentence actually follows the previous sentence. So this is good for tasks such as QA. And you can fine tune or use these kind of embeddings that you get from the model for other tasks. So for kind of like a simple baseline and a lot of the SLU or NLU tasks, you can probably use a large language model, find the embedding for that, pass it through some sort of machine learning like LSTM or something like that, and get your preliminary results. So next I'll talk about the dialogue manager. So I don't do too much work here, but there is kind of this main task of dialogue state tracking. So what dialogue state tracking does is it keeps track of the user's goals or information in that conversation. So for example, maybe like what hotel they want to book if they mentioned it previously in the conversation. So a data set that researchers use here is multi-WAS, and this consists of human-human conversations over multiple task-oriented domains where one human believes they're talking to a system, and then these are annotated for those kind of user goals. And then lastly, there are some ways of doing natural language generation. So there is kind of a retrieval way and a generation way. So with retrieval methods, you usually have access to a large corpus of conversations, and you would search for the conversations that are most similar to your current conversation based on some sort of metric. This could be maybe a similarity in the conversation context, in various ways of calculating that. So then once you pick a conversation that's similar enough, you can use the response in that conversation as the response for your current conversation. So with the generation method, you would use the language model to generate a response itself based on that context. Another area to explore kind of here is style. So you could want the system to say something angrily or maybe in a Shakespearean way or any of those kind of style methods. So there's also other ways, there's also other interesting areas of exploration here. So a big thing for generation is that sometimes the generated responses are not factually correct or consistent with the things that the model has previously said in the conversation. So if anyone has played with ChatGPT, sometimes it definitely gives wrong facts, or it contradicts itself, and that's not something that it knows how to correct. So controllability is also another big area, since you might want to include certain bits of information in your generation, or you want to make sure that your model is not saying anything toxic. Explainability also plays a big role, as if the system can explain why it says certain things or makes certain decisions, a user could be more likely to trust the output from the system if the system is telling it to do something or booking something for them. And lastly, evaluation, which I'll talk a little bit more in depth now. So here with evaluation, there's multiple challenges that are associated specifically with dialogue. So one is the large context, which I talked about before, that you need to take into consideration. There's the multiple speakers throughout the conversation. So the example I showed with Eliza only has 2 people participating, but it could have more than 2 people. Then we also have the one-to-many response problem. So here, this means that there could be many correct responses to a dialogue, and there's no one correct way. However, these standard language generation metrics, such as blue or rouge, require this reference response or this gold response. And so blue and rouge look at the word overlap between the generated response and the reference response. So another thing here is, so there's 2 ways that we usually do evaluation. There's human evaluation and there's also automatic evaluation. So for human evaluation, of course, you can ask a human, oh, how good is this response? But then what does good really mean? Good could mean multiple things. It could mean, is this interesting? Is this engaging? Is this fluent? There's a lot of different definitions. And so it's important to kind of ask in more specifics. So that's why when we work with automatic evaluation, we actually look at these kind of fine-grained metrics instead of just saying, oh, is it good? So as I said, gave some examples, but here also coherence or fluency. So I actually published something recently about using large language models for dialogue evaluation, where we actually use prompting to prompt the language model to generate a rating for a certain response. And what prompting is we give a large language model a few examples and ratings for those examples. Then we give it a test point and ask it to predict a rating. So we do this because we don't want to fine tune these really, really large language models, which I'll talk about a bit about later. So the largest one that I've worked with is 530 billion parameters. And that's like compared to like GPT-3 is 175 billion parameters, as a bit of a comparison. So I'll move into talking a bit more of speech tasks. So these are some of the speech tasks that researchers work on. So automatic speech recognition, or the ASR, text-to-speech, TTS, speech enhancement or separation. So what this is speech enhancement is improving the overall quality of the speech. So if there's a lot of background noise, say that you're filming outside on the street and there's a lot of cars going by with the noise, you want to separate the person speaking from that background noise. And that is also similar to speech separation. So it could either be separating the background noise, or it could be separating one speaker from another speaker. We also have voice conversion. So with voice conversion, we convert one person's voice to another person's voice. We have spoken language understanding, which I touched a bit about before. And we also have speech translation, which is translating kind of speech instead of translating text to another language. So these are some tools for speech tasks that I think would be helpful if you ever want to get into this space. So the first one is Caldi. So Caldi is a speech recognition toolkit, and I use it a lot for kind of the speaker identification, speaker verification tasks as well. So I guess I didn't talk about that, but speaker verification is when you're verifying if one piece of speech is actually spoken by one person, and speaker identification is identifying who actually said that. There's also ESPNet. So ESPNet is an end-to-end speech processing toolkit. This actually came out of a lab that I'm currently in, and it supports recipes for the task that I mentioned on the previous slide. And it's a great place to start playing around with speech tasks if you're interested. So a little bit more about the problems in ASR. So for the background noise, there are various recording conditions, as I talked about before. So with the clean ASR data sets, they're usually collected in, potentially a soundproof room, person is next to the mic, no background noise, and so you're only really focused on the speaker. But that's not usually the case in a lot of the other data sets, where you could be potentially in a meeting and the microphone could be at the head of the table while someone is all the way at the other end of the table. So you still want to capture what they're saying. And also, if somebody is outside, somebody's in noisy conditions, these are all things to consider. And it does degrade the ASR performance. Another thing is the different speakers. So there's a lot of languages, and ASR works relatively well on English and other high resource languages, but for the low resource languages, there's still a lot of work to be done there. There's also accented speech. So for standard American English, ASR systems work really well, but then when you add accents into there, it could change the way that some people are pronouncing phonemes or pronouncing words, and the ASR model will still not be able to recognize that. There's also disfluencies. So this happens more in dialogue, where you have the back channeling. So what back channeling is when someone says, yeah, uh-huh, or maybe you're interrupting someone in saying that. And so you need to be able to pick that apart when you are doing that ASR. So I know you guys talked a little bit about hidden Markov models. And so early models for ASR actually did use hidden Markov models. So what they did was you can split each word into a series of phonemes, or these sound units that make up your language. And each sound is influenced by the sound before it and the sound after it. So each phoneme is represented by this 3-state hidden Markov model. So after talking a little bit about speech, I'll talk some about these current large language models that are available. So large language models are mostly, if not all, transformer-based. And so these are some of the language models that are of interest for various reasons. And some of these are available on Hugging Face. which has many pre-trained models and data sets that you can explore with if you're interested. So the first one we have here is Bloom. So Bloom was trained, I believe, over 46 languages and some coding languages as well. And it's really focused on the multilingual aspect and being able to be used for different languages. We have Piano GV2, which came from Microsoft, and it's one of the largest models at 530 billion parameters, and it's trained on a lot of web scraped corpora. We have GPT-3, so a recent one here is Instruct GPT, and this is fine-tuned with the prompting dataset. So it's really good at, if you give it instructions, it can do a task quite well. And you also have FLAN-T5. So FLAN-T5 was like a transformer that's fine-tuned on many NLP tasks. I think it's 1,800. And so it does really well in generalizing in that aspect. So here are some of the applications that use large language models. So one of them that I found recently was Elicit. So what this does is it uses models, mostly variations of GPT-3, to find and summarize related research. If you're trying to find related works for any of your projects, this is probably helpful. We also have ChatGPT, as all is the rage these days. And then we also have DALL-E. So this is not necessarily like a large language model, but it generates images from text. Yeah, so the last thing I wanted to talk about was like ethical concerns in using these kind of models. So one of the largest things is bias in the training data. So as I said before, a lot of these large language models are trained on data that was scraped from the internet. So these are a lot of things that you can't really account for in the data. You can filter it, but you can't filter for everything. So there's one worry that the model is going to propagate the bias that exists in that training data. Another thing is that the model can say something toxic due to the training data. So of course you can filter it for kind of those toxic words, but you can't really catch everything. And also, what does it mean to be toxic? That is still kind of like depends on a person-to-person basis, and it's still being studied. Another thing is that generated outputs can be used to scam people. So if you've used GPT-3, not GPT-3, if you use ChatGPT, sometimes it does say like, oh, I'm a model, don't take my word as like the only truth, that kind of thing, to present itself as a model. But for these kind of things, you can kind of just take off that label and you can use the generated output and whatever you wish. It's a little bit more difficult in speech to actually have these kind of labels. Of course, you can say at the beginning, like, oh, I am still a robot. I'm a robot. Please remember I'm a robot. But then you can still take the rest of it and use it to scam someone, maybe do voice conversion, convert it to the family member of the person you're scamming, convert it into a famous politician or anything like that. So that's kind of scary, and it's still an open field for research. So hopefully more results can come from that. Oh, and that's the end. So thanks for listening.
Thanks, Jess, for the overview of like an entire field within like 10 minutes. Really appreciate it. Are there any questions for Jess? Yeah. So I don't think you heard that, but
Definitely not.
she asked what you meant when you said that DALL-E is based on a language model.
Yeah, no. So I included that, and it's like not necessarily a language model. I just wanted to include it since it's like one of the things I feel like people would have seen. It does like generate images from the text, but it's also like based on kind of this like transformer architecture, I believe.
It uses the transformer thing to encode text into like image generation, right? But I guess it's not technically a large language model.
It's like not technically, but yeah, it's just another example of something that people have probably seen. Yeah.
Any other questions for Jess? Cool, great, Jess. Thank you for the presentation. I'm sure now when if they want to work with anything speech or dialogue related, they'll know what to look for. And yeah, that's Jess's email on there. I'll also post it on Piazza. So if you want to reach out to her and ask her anything about the seal or anything about her research, I'm sure she'll be more than happy to answer.
Okay. Yep. Feel free to reach out to me. Like anything about like graduate student life also like would be open.
Yeah. Okay. Great. All right, thanks, Jess. We'll just leave the meeting now.
Okay.
All right. All right. Okay, that was great. Yeah, I was I was trying to put together slides on this kind of field, and I was like, yeah, I actually don't know anything about this, so I gotta bring in an expert. So I'm glad she was able to talk to us about that. Okay, great. I hope you thought that was informational, and hopefully, if you want to do any kind of projects in that field, look for and what kind of things you want to work on. So we're going to spend the last 35 minutes here on transformers, and that's enough time, so that's great. So this was kind of requested, and this is very much in the news, and this is blowing up not just for NLP, but also for other kind of satellite tasks. So I think it's definitely worth learning about. It's also a different kind of framework of deep learning architectures. So in that sense, in the sense that we covered convolutional neural nets and we covered RNNs, this is also worth covering because it kind of works on a completely brand new paradigm. So hopefully you find this useful, and we can kind of learn about this kind of model architecture. Okay, great. So I'm going to start off by talking a little bit about sequence-to-sequence models and just kind of refresh your memory on what we've talked about so far and what kind of task motivates this kind of model architecture. So sequence-to-sequence is a really common ML task, especially for natural language processing. And it's exactly what the name implies, right? It's given some sequence, predict another sequence. So, given a sentence, predict another sentence, given, whatever else, just given some time series information, generate some other time series information. But the major thing here is that the lengths might be arbitrary, right? So your input sequence and your output sequence might not exactly be the same length, right? And I bring that up because we've talked about recurrent neural networks before, where we saw this kind of model architecture where given some input, right, using some recurrent hidden states, and in this neural network architecture, we can also retrieve some output sequence, right? So you could say that an RNN alone could be sequence to sequence, but if you use it this way, then you're stuck on the length of sequence you can generate based on the input, right? We want some kind of architecture that's independent in terms of the sequence that goes in and the sequence length that goes out. Also, I should note, if you were trying to do, let's say, language translation with something like this, when you start translating the first word, you've only seen the first word to translate it, right? So you can see, just going directly like this has a lot of different limitations. And so this kind of developing these kind of architectures and models has a lot of applications in language translation, question answer, which Jessica talked about, where we pose some question to the model and the model answers with some response, and then also in text summarization, where you input some long paragraph and it outputs one or two sentences that summarizes the contents of that paragraph, and that's a real high disparity in the input and output sequence lengths, right? So what was the kind of main thing before transformers were these encoder-decoder networks, and I'll walk through this diagram. So first, what we do is instead of just using an RNN to go straight into some output, right? We first show some encoder RNN architecture the input string, right? And so we have text here. You do have to do some kind of input word embedding, so like you could use word2vec for that if you wanted, right? But you have some, or you can do bag of words, or even like one-hot encoding of the words, whatever. But you have the sentence, input sentence, you have this input word embedding, right? And then you feed that into some initial RNN, and it gets to see the entire sequence first, right? And what you're left with is this hidden vector, right? So you end up with one vector at the end that kind of represents the content of this entire sentence after you feed it in. And then afterwards, you have another RNN that's a decoder RNN that then takes that hidden vector, then generates the output, right? So just given that hidden vector, it generates I, and then we feed that back into the decoder just to provide context, just to tell it, remember, this is the last word that you just output, and then it kind of feeds it back in, generates the second word, feed it back in, generates the third word, et cetera, et cetera. So this is kind of the most common framework. This encoder-decoder framework is the most common was the most common for these kind of tasks. And there's variations on this that you can do, right? So for example, down here, instead of just showing the previous output, you can also provide the input here. So almost like a skip connection, right? So that the model has more context when it's decoding the target output. So you can use, again, this is really flexible. You can use this for translation. You can use this for whatever, tagging, a lot of different sequential NLP tasks. So one thing that happened with this kind of encoder-decoder networks is you'll notice that the entire input sequence needs to be stored inside this hidden vector, right? So there's this bottleneck. There's this bottleneck between the encoder and decoder that requires all the semantic information that we need, that task-oriented information we need, to be just stored in that middle vector there. And this can be a pretty big limitation because we're asking the model to really do a lot. So the solution then is to instead allow the model to focus on different parts of the input when predicting, instead of having to look at everything all the time, right? So instead of just looking at that input vector that contains all the information possible about that entire input sequence, we can just say, for this output that you're generating now, what's most relevant to you that was in the input, right? And we can do this using an attention mechanism. This is where attention mechanisms came from. So in its most basic form, right, we have some decoder state, we have some encoder state, and the attention function spits out, how relevant is this encoder, are these encoder and decoder states, and gives it an attention score. And based on that attention score, the decoder model can decide what kind of outputs to generate. And so kind of implemented in the rest of that original diagram. So again, you can ignore this top half, everything else is the same, right? But here, every time it generates this word, right, we're checking over all of the inputs and seeing which inputs are relevant for the decoding that I'm doing right now, right? And so we take this, we do the attention, we do softmax, and at the end, that vector tells you, hey, for the word that you're decoding right now, I think that these input vectors are the most relevant, right? And therefore, the model can pay attention to just the relevant information when generating its next word, right? So for example, for translation, let's assume, for example, that I'm translating, I don't know, English to French, right? English and French, well, no. English and French are actually quite, I don't know. I mean, Asian languages are quite difficult for this, especially. So let's say I'm translating from English to Korean, right? So English and Korean have noun and verb orders flipped, right? So the verb and the noun come in different orders between English and Korean. So you would imagine that, when I'm on a verb, when I'm decoding a Korean verb on this end, it would be useful to say, well, the English verb was over here, right? So you don't have to pay attention to all this other noun stuff. Just pay attention to the verb that was in the encoding step, and then use that to make your decoding. So that's kind of the intent of this attention step. All right, any questions so far about sequence-to-sequence, encoder, decoder, and attention models? Yes?
This model requires a fixed length. But the language is can't just take the language sentence.
This doesn't require a fixed length.
So you have limited.
No, this is an RNN here. So you can feed in as much as you want into this. You can just, these are shared weights, right? So if you recall during our RNN lecture, right? Each of these aren't different layers. Like this is the same thing, right? And then we're just applying the same thing to each token in the sequence, just with some hidden state transitions in between, right? So an RNN input can be as long as you want. Does that make sense? Okay. Yeah, it's just, yeah, we're just, yeah. Right. And then on the output, the model itself decides when to stop. So it keeps going until it outputs a stop token, actually. Yeah, which is this EOS tag here. And so the model itself needs to learn not just what words, but when to stop. Any other questions? Sequence to sequence encoder. Okay. So based on this work, turns out, so we have this combination now of recurrent networks and this attention mechanism, right? And this was actually like a huge deal for a while, and this was like state of the art for a few years. Especially, and one thing that was especially useful is not only do you get kind of better performance, right? Because you can do these sequence-to-sequence stats, because a deep learning model, you can make these parameters as large as you want, right? And attention kind of makes these parameters more efficient, right? Because it doesn't have to look at everything all the time. But also, you kind of get a quote-unquote explanation for each word that's decoded, right? Because by virtue of this attention mechanism, you can actually say, well, when the model generated this word, right, it actually looked at these words in the input to generate that output, right? So, for example, if this is if we kind of formulated this in a semantic kind of a way, so if we're trying to ask this model to say, is the sentence happy or sad or whatnot, we can actually say, well, the reason it said it was happy is because it looked at these words, right? So it kind of gives you an inherent explainability thing. There's a lot of research now that says attention is not explanation and explanation is not attention. So this is controversial, but naively, you could interpret attention as interpretability, right? Actually, I think that's the title of the paper, is attention is not explanation or something like that. But anyways, okay, so after this, so now we're going to get into transformers. We've set all the groundwork. So after this work, what some researchers at Google Brain, or Google AI, one of those two, found out is that you actually don't need the recurrence at all. The only thing you need is attention. This attention mechanism is the only thing you need to learn a good sequence-to-sequence model, or learn a good language model. And in fact, that's the name of the paper that they released. You can tell that I've said this before, but this computer science field really likes catchy titles or like memorable titles, but it helps, right? Because that's how you kind of communicate your work. But the title was "Attention is all you need," and again, you don't need recurrence, you don't need convolution, because convolution was another kind of one-dimensional convolution was another example of doing these kind of models. Turns out all you need is the attention mechanism. So these kind of, and we call these architectures that use these what we call self-attention mechanisms without recurrence or without convolution. That's what we call transformers, right? And now we're going to go through this architecture step by step. We're going to walk through this self-attention mechanism, and we're going to understand why this works and why it does state-of-the-art performance on most NLP tasks. And in fact, it's actually more computationally efficient than RNNs. So we kind of get both. We get better performance, computational performance, and we also get better task performance. And not only that, and I'll discuss this at the end, but and Jessica also discussed this at the end, where she says, you can use these large models, these transformer-based models, on anything you'd like through prompting, right? And we can these are really, really, really high capacity models, and this is what kind of enables that. Okay, so let's start by talking about self-attention. So this, like I said before, this self-attention step is this fundamental operation of transformers, and this is what underlies like all of that initial like performance gain. So, given some input vector sequence X, and we're trying to generate some output vector sequence Y, right? So this is kind of a traditional seek-to-seek. What attention does is it just generates Y as a weighted average over the input sequence, W, right? So assuming that this W sums to 1 over J, right? It literally just it just runs WX and sums it over J in order to generate Y. So it's just WX, right? But the important part here is that W is not a learned parameter. W is the covariance matrix. Not the covariance matrix. Well, kind of the covariance matrix. But the parameters in W is just Wi times Wj, right? So W here is completely learned from the kind of the input data. It's derived from the sequence X, right? And by the way, I should mention, a lot of times we're going to talk about this as an input vector sequence, and that's because I'm assuming that each word is a vector, right? Because I'm assuming that there's some embedding that exists, right? So each X is a vector, and that's why the notation is going to look like that. But again, so for each sequence, you multiply each word by every other word, essentially, and that defines W, right? And so for each input X, so for each input Xi, we're going to call Wij times Xj. So we're going to multiply that corresponding row in W by every other word in the sequence, and we're going to take that weighted sum for the output Yi, sorry. So the one thing to note here is that all elements of the sequence interact with each other at this self-attention step, right? So previously for the RNNs, right, we only had everything we've seen up to that point through the hidden states when we're predicting each output, right? Whereas in this case, we get to combine information from all the other inputs throughout the entire sequence when we're doing the self-attention. Okay. So to show this graphically, I stole this off Peter Blom's fantastic blog post. By the way, I will post the blog post that I'm taking explanations and figures from on Piazza afterwards. He has PyTorch code to go along with each step of the way. So you can write a transformer from scratch in PyTorch if you're so interested, right? But it's a fantastic post. But again, so let's go over this. So for some given x, we're at x2 right now. We're trying to generate y2, right? So for some given x2, we're going to take this x2, right? And we're going to multiply it by every other vector, right? So we're calculating W, we're driving out W now. So W21 is x2 times x1, W22 is x2 times x2, W23, etc., right? And then you're going to take the product of that with each of the vectors, right, of the input vectors, and that serves as your output. So what's the intuition here? The intuition here is I'm checking how relevant this input X is with every other word, right? So this is the attention, right? This is I'm attentioning on myself, basically, on my own sequence, and then I'm using that to determine what my output should be. So one thing you might notice is we have not talked about learned weights yet. There's no learning yet, right? This is just self-attention, right? So given some input vector X, we can do this. And the reason this works is the same intuition as actually collaborative filtering and matrix factorization, which is, where we did given only user movie pairs, it was able to learn some lower dimensional user and movie embedding to do its task, right? To do its recommendation task. Same thing in the transformers. What we're learning is the word embeddings, right? We're learning the embeddings such that their dot products express how they're related to each other and how they should attention on themselves in order to generate this output, right? So the dot products between these word embeddings are going to express their relationships to each other. And so and that happens in the embedding layer. So if we really, take this back all the way to, so we're right now just focusing on transformers, but if we kind of take this into context in terms of transformers in an NLP task, right? You would have some words. You would have to convert the words into some kind of embedding, right? And then the embeddings come into here as vector X's, right? In transformers, you are learning that embedding mapping, right? So usually actually how it comes up is words will be tokenized first. So some system will map words to like a bag of words or tokenization scheme, whatever. And then it goes from that into an embedding using some learned neural network, right? Some MLP thing. And then that comes into this transformer and it does all the embedding, you get your output, and then the loss propagates through the entire thing to update and learn this embedding. So again, right. Oh, there we go. Sorry, I'm like flipping through slides. Okay, does this self-attention kind of make sense so far? Right, so again, the attention thing itself doesn't have any learned parameters. It's the embeddings that matter. We're learning the embeddings so that it can take full advantage of this self-attention mechanism. And every part of the sequence is contributing to the attending at each step, right? but only in this self-attention block. All right, we're going to expand on this a little bit. We're going to get a little bit more complicated. This is the simplest iteration. The one thing that I want to point out first is position. So right now, self-attention, the way we've presented it so far, is order agnostic, right? So I like dogs is equivalent to the model as like dog's eye, right? And in our fancy language model, we would like that to not be the case because order really matters in sentences. So what we can do is we can just encode position information and concatenate to the word embedding, right? So before we had some vector x for each word, and now we just append like 1, 2, 3, 4, or like a longer vector, or whatever is more appropriate for your task next to that word. And you'll see this quite a bit. We can just concatenate embeddings or concatenate representations together, and then we can feed them through a neural network, and it'll do just fine, right? But this is how you take care of the fact that words in a different order are different. And in fact, you can actually get the model to learn the position embedding, right? So you can say, hey, this word is in 2, and then it does a neural network into some vector, right? And then the model itself learns what that embedding should be. So that's entirely possible, and that's just one more parameter that gets learned. Or you can do some fixed encoding, some fixed mapping from the position of a word in a sentence into some numerical representation or some vector representation. Going even one step further than that, you'll notice that vector x is doing 3 jobs right now, right? So each vector x gets used here, here, and like up there too, right? So the first way that it's used is first compared to all other x's for its own output, y, yi, right? So for when we're generating y2, x2 gets used in order to generate y2, right? So we call that step the query step, right? And then this y2 also gets compared to all other x's for all the other outputs, right? So when we're generating y1, y3, y4, it gets used here, up here, right? To compare all those other inputs to it, to this appending mechanism. So we call that the key. And then finally, it's used as a part of the weighted sum. So we call that the value. Oh, and again, that gets called the value. So that's that. Fine. So then flip 1 and 2 and 3. So the same embedding x is being used for these 3 different jobs: the query, the key, and the value. And this key value comes from like nomenclature from the previous attention mechanisms, where they're like from like key value pairs. You don't need to worry about that. Just know that there's this like query, key, value steps that this embedding is being used for. Now this is actually quite a bit of work for one embedding to do. So what we can do instead is we can learn some linear transformation, W, right? And this is truly just a linear transformation of x into different representations to be used at different stages of this self-attention mechanism, right? So instead of using the same x for the key value query, we can now generate a query vector, a key vector, and a value vector. That's each a linear transformation of x, and this gets learned as part of the gradient back propagation process. So now we can rewrite those kind of expressions we had before, but using these 3 different variables instead of using x every single time. And this adds expressibility to the model. And kind of the intuition here is when you're going up this path, that's different from comparing, like the embedding that you use to compare with other words should be different from the embedding that you use to generate your output, right? That's kind of the intuition there. Okay, right, so now here's the new diagram. It's the same exact thing, except now there's 3 different colors, right? So we have some original x, and then so we transform that for the value, transform that for the key, and when it's being used for some other output at some other position, you'll use the query linear transformation. All right. Going multiple steps further, words can relate differently depending on context, right? So if we're comparing to a word gave, right? The word Mary here is the person doing the giving.
word roses is the object being given. To doesn't have any relation to gave at all, and Susan is a person receiving the roses, right? So the kinds of so before we can measure the magnitude of the relations, right? So this attention mechanism with these dot products, we can say Mary relates to gave a lot, and then to relates to gave little, right? But we'd also like to represent how, right? How, like, not only do they relate more or less, they relate differently, right? So we'd like to capture that as well. And we can do that with multi-head attention. So instead of doing attention once, we do it multiple times, right? On this X, and we learn a different query linear transformation, Q, K, and V, for each head R, right? So it's just we just do attention multiple times, right? And this is actually computationally not too bad because it's just matrix multiplication. So we just expanded on one axis so that we can do this multiple times, right? So you might imagine that one R, I don't know, learns the direct object relationship, and another R learns the noun-verb relationship, right? So kind of things like that. So we're continuing to add capacity of this model to really, truly learn relationships between words, because that attention is the whole thing that's doing the learning here. There's no recurrence, there's no convolution, it's just the relationships of words to each other. And we're maximizing the capacity of the model to express these relationships. Do you have a question? Yeah.
How is this different from the current network that you have again, in order to have different types of different R's?
Mm-hmm. So in the recurrent neural network, the core
kind of element of the thing that's giving it the sequential nature, right, is we're calling this on each input sequence. And then the recurrence is this almost memory, right, this hidden state that stays between the nodes, right? So for an LSTM particularly, you have this long-term memory that goes all the way through, right? But the thing here is that this output only knows about this input, right? Not only that, it only knows about it because of this recurrence relation, right? Whereas in this attention, there isn't any recurrence here, right? Each output is a product of the entire input at each step. There's no recurrence. It's just each output is just a product of its inputs. Literally a dot product of its inputs. Yeah. So it's an entirely different model architecture. Maybe? Yeah, maybe. Okay. So I guess let me try and explain that a different way. So a recurrent neural network, so a recurrent neural network, the core concept is it's sequential. You need the previous output in order to generate the next output, right? And then you need that previous one to do the next one. This one doesn't. This one looks at the entire thing at once. So you can actually run all this in parallel. There's no sequential concept here. There's no concept of a sequence. It's just input-output, right? But they were able to cleverly set up this attention mechanism so that even though we're generating the output all at once from the input, it's comparing itself to itself. And so it's able to learn the relationships between the words in its own sequence, right? Does that make a little bit more sense, maybe? But that's the core difference. It's the difference between the sequential and not. We're getting rid of that recurrence assumption and replacing it with attention. Okay, so as a quick recap, we can use attention to learn word embeddings such that dot products express word relationships. Yeah, sorry, go ahead. Yeah.
So are you saying that there are, are you saying that there are like multiple heads that are then concatenated and down?
Yes, they do that. Yep. So imagine like this. we have these W's that project it into each vector, right? Imagine this extruded in this direction, right? So then you get a bunch of these arrows coming out, and then yeah, you would have to use something to then, you would use like an additional neural network to compress that back down into the dimensionality that you need. Yeah.
I could be wrong. Literally all my knowledge of this just comes from errors.
Sure, totally fine.
But isn't it that you split it up by channel first, then you kind of do like, for example, if you have like a 12 vector embedding. Like,
Sure. So let's say this is 12 length.
Yeah. You split it up into like, let's say 4 different like vectors.
Yeah.
And then you do attention between each of those 4 that you split up, and then you concatenate them at the end.
So that's one way to do multi-head. This is the naive multi-head. I think you're talking about like the more computationally efficient, because this multi-head that I'm talking about scales linearly with the number of heads that you have, and that gets computationally expensive. So yes, you would do that for, and that's in the blog post. I just skipped it. yeah, good point. Yeah, you know what I mean. Yeah, but for this naive implementation, you would just repeat it. But yeah, you would split it if you were doing. Yeah. No, I think that post that I'm going off of kind of did it this way because intuitively this makes a lot more sense, right? I think when I first heard about the splitting, it's like, well, you're not even seeing the entire embedding, but then you're learning the embedding, so it doesn't really matter anyways, right? So yeah. Anyways, okay. So again, here's the self-attention, and now we're going to move on to the transformer block. So the rest is actually really straightforward. This is the hard part. The transformer block, you just get the input, you do self-attention, you have some layer norms. It's just batch norm. It's a layer norm instead of a batch norm, and then you have these MLPs, and don't get confused because there's multiple. We just feed it through one like fully connected neural network, multi-layer perceptron, and then we get your output, right? And then there's all these skip connections because we showed, especially in kind of ResNet, that these residual connections are really helpful for maintaining information, so that you don't lose too much going from one step to the next, right? So we just straight up concatenate these representations with the output from the self-attention, feed that into some neural network, concatenate it with that, and then and then we get the output. And the neural network magically figures out what's relevant, what's not relevant for doing the task at hand. Okay? Yeah, this box here is the hard part. The rest of it is just kind of not formalities, but it's a kind of a construct to be able to stack these together, right? So let's look at an actual concrete example, which is classification. So if we wanted to do sentiment analysis, right? Let's say, is this a positive or a negative rating on IMDb, right? So if we get some input, this movie is great. First, that goes into a word embedding, right? Again, this is learned. This is a learned embedding as part of this whole transformer model process. And then you add on this position embedding. This can be either learned or encoded. Very commonly learned because it's easy, right? You just slap it in there and it does back propagation, right? And then you stack it through a bunch of transformer blocks. You get your output sequence. You average it. This is like average pooling in CNNs too. You just average it. You get a positive or negative output vector. You calculate the loss against the target. So it's a very, very end-to-end model, right? Like every step here is learned, and this whole thing just gets gradient propagated all the way through, and it works, which is fun. Let's look at another example on text generation. So this is another example, right, where let's say translation, right? In this case, the input sequence are characters, right? And let's assume we're working with some Latin language where you can do this kind of character-based thing. So the input sequence are characters. You have the word and position embedding. Again, slam it through the transformer blocks. You get the output. The output sequence gets converted into character probabilities, and then you can have your output character sequence. Now, one thing that I should note is that transformers, again, look at everything, right? So there's no recurrence. So there's no like it's at each prediction, It can look at everything before it, and it can look at everything after it. And so self-attention needs to be masked to prevent the model from just, when you're training this, it needs to be masked in order to prevent itself from looking forward, right? We're just cutting off some arrows, essentially, in that previous diagram that I had, so that this generative model kind of thing works. Because otherwise, the model will just look ahead and go, oh, there's a sequence, right? Especially if we're trying to ask it to, like, here's the input, predict the next word in the sequence. Well, it can see the rest of the sequence because it's not an RNN, right? And so you kind of need to do some masking tricks to make sure that it doesn't just look ahead and cheat. That's, you don't have to go into the technicals in that. All right, so let's finish up with kind of large language models here. We're coming up on time. So the original architecture was still this encoder-decoder construct, just because that's what everyone had been working with. But state-of-the-art says you actually don't need to do this anymore, right? You either only need the encoder block or you only need the decoder. So you either only need this stack or this stack, and the stack can be as deep as you want it to be because you can just stack transformers end to end, and it does just fine. Okay? All right, so I'm going to spend the next 3 slides just talking about GPT-3, which Jessica also mentioned, because this is like the biggest kind of example of a transformer model kind of beating everything else, right? So GPT-3 is a 175 billion parameter language generation transformer model. It is 96 layers, so 96 layers of these transformers blocks that I just discussed. The inner state is 12,000 dimensions, which is crazy if you think about it. And then it has 96 128 dimensional attention heads, right? So it is a massive model really designed to learn as much as possible from a massive corpora of data, right? And in fact, it's so large that their batch size is 3.2 million, right? So each feed through, they were feeding through 3.2 million sequences during each backpropagation step, right? So the kind of hardware and the kind of compute necessary to train a model like this is immense. And that's why we're also having the kind of accessibility discussion, right? Can you even participate in this research field if you don't have the compute necessary to do things like this? Which is why there's been a lot of effort on low compute, low resource models. And in the GPT-3 paper as well, they discuss a lot of different models, and they fully quantify the trade-off between compute, data size, and the kind of performance that they got. And if you actually go on Hugging Face, you can download this, which is nice, or you can train a smaller version of it yourself and whatnot. But again, in the end, this kind of model is a generative model, right? So it's text generation model. So in the end, it's just modeling the probability of a word conditioned on all previous words, right? So even if it's doing transformers, the fundamentals stay exactly the same. We're just doing this prediction. Yeah. Yeah. So, to my understanding, it goes 96 this way, and then wait, how many layers? Hold on. How many heads were there? There's 96 heads, and each head is 128 dimensional. So each of these is a head. So you have 96 this way, and I think the 128 is referring to that splitting implementation that you were talking about, and I didn't discuss that today. But if you go on the blog post, it'll explain that. Yeah, but I just thought that was a little bit complicated or unintuitive, so I just skipped it. I'm also out of time, so yeah. Anyways, so it's this massive model, and in the end, again, it's just text generation. So they just gave it sentences, and it said predict the next one. There's a lot of nuance into the kind of encoding and stuff that they did, but the big thing that we're starting to learn from this is that we can train these large language models on massive corpora, and it just becomes this extremely general model that we can use to do zero-shot learning, where we don't even give it an example, one-shot and few-shot learning, where we don't have to retrain the model in order to do different tasks with it. We just have to do clever prompting. This is what Jessica was talking about when she said prompting, right? Literally prompting as input to the model, translate English to French, and saying, here's my input, cheese. There's no input thing in the model, right? This is just a sequence that's given to the model. But the model itself is so good at modeling language that it knows what you want, and it's going to fill in the next word with the correct answer, right? So that's kind of the power of these large language models, and that's what the hype is, and this is exactly what ChatGPT is doing, right? And the same thing with one shot, right? You give one example of what you want, and then it'll fill in the rest. And then few shot, where you need to give it a few examples, and it'll provide the output. So it depends on how kind of obscure the task is, or how well the task was represented in the learning corpora. But you'll actually see in this paper, if you ever read the GPT-3 paper, you'll see how this model compares with other models that were specifically trained to do these same exact tasks. And quite often, and not always, but quite often, it'll outperform other models that were specifically trained to do these tasks, just by nature of being a large language model and having a fuller, better understanding of the language. So quick, last slide, quick recap. GPT-3, state-of-the-art language processing model by OpenAI with 175 billion parameters. And this transformer architecture is really what enabled it, right? It's using GPT-3 and BERT and other NLP models as well. And GPT-3, again, this unsupervised learning technique where we just feed it text data and it's able to formulate a problem to learn the language model. And it's really capable of generating human-like responses, even if you're doing one-shot, no-shot, few-shot learning tasks. And so, you can safely say that transformers have revolutionized natural language processing, and I wrote that slide with ChatGPT. So, anyways, thanks for coming to lecture and staying 5 minutes over. I think that's the last core lecture slide. I'm going to try and squeeze in another lecture next Thursday if I can. I'll have updates on Piazza, but this Thursday, definitely, we're having an interpretability and explainability and machine learning lecture by Dr. Lucas Mandrake. As you know, he's a great speaker from his first lecture. And then the Tuesday after that, another lecture by him. Thanks. Also, I have ChatGPT Plus, I have the subscription, so if you want to play with it after class, just come up to the podium and you can type anything you want.